Have you ever stopped to think about what's really happening when a computer looks at the code you write? I mean, how does it take this jumble of symbols and turn it into something it can actually do? Well, today, we're going to gently pull back the curtain on one of the most elegant ideas in computer science that makes it all possible. It's called syntax-directed translation.
So let's start with something super simple. Take a look at this. 9 minus 5 plus 2. You and I, we just know how to solve this, right? Our brains just do it. But for a computer, this is just a string of characters. A 9, a dash, a 5, a plus, a 2. So how in the world does it make any sense of it at all?
Yeah, that's the big question, isn't it? How do we get from symbols on a screen to a meaningful action, a real calculation? The answer? Well, it's this really beautiful and powerful technique. And as we saw in the first slide, it's called syntax-directed translation.
All right, let's zoom out for a second and look at the big picture here, going from symbols to actions. It sounds kind of abstract, but trust me, this is one of those foundational ideas that quietly runs so much of the tech we use every single day.
So when we think about this stuff, our minds usually jump straight to compilers, right? The things that translate Python or C++ into machine code. And yeah, that's a huge part of it. But this idea goes way, way beyond that. It's really a master key for understanding and translating any kind of text that has a predictable structure.
And when I say it's everywhere, I really mean it. Of course, you've got your program translations, that's the compiler stuff we just mentioned. But think about this. The same core idea is used for designing computer chips. A description of a chip gets translated into an actual circuit design. Or how about databases? When you write an SQL query, this is the magic that helps the database figure out exactly what you're asking for. It's pretty amazing how versatile it is.
Okay, so where do we even start with all this? Well, it begins with a blueprint. Just like you can't build a house without a plan, you can't translate a language without first defining its structure. And that blueprint is called a grammar.
So, step 1, before we do literally anything else, is to lay down the law. We need a set of rules, the grammar, that describes what a valid sentence or expression or program even looks like. It's the skeleton that holds everything together.
And the tool we often use for this is something called a context-free grammar. Now, don't let the name scare you. It's really just a fancy way of saying we have a set of rules that helps us break down big, complex things into smaller, simpler pieces until we're left with just the basic building blocks.
Here's what one of those rules might actually look like. This little arrow thing is our rule. It's called a production. And all it's saying is, hey, one way to make an expression is to take another expression, stick a minus sign after it, and then follow that with something called a term. And by just stringing together a few simple rules like this one, you can map out the entire structure of our little math language.
So, now we have our blueprint, our grammar. What's next? Well, a blueprint is just lines on a page until you add notes about what materials to use, right? So now we're going to start adding meaning. We're going to write notes on our blueprint.
And we do this by attaching little pieces of information to the different parts of our structure. We call these attributes. And they can be anything really. If we're looking at 9 minus 5, an attribute might be the numeric value. If we're looking at code, it might be the data type of a variable. They're like little sticky notes we put all over our grammar.
One really common type of attribute is called a synthesized attribute. Again, fancy name, but a super simple idea. It just means the information flows up. Think about it. To get the value of 5 plus 2, you first need the values of its kids, the 5 and the 2. The final value is synthesized or built up from the pieces below it. Simple as that.
And this is how we specify how to calculate an attribute. This is called a syntax-directed definition. It's a rule that basically tells us what the translation should be. So for this one, it's saying the translation of our expression, that's expr.t, is going to be the translation of the first part, followed by the translation of the second part with a minus sign tacked onto the end. It's just defining the final result.
Okay, we've got the structure, and we've attached some meaning. But now for the final piece of the puzzle, we need to add the actions. We need to specify not just what the translation is, but how and when to actually do it. And for that, we use something called a translation scheme.
So here's the big idea. Instead of just describing what the final output should look like, we can literally embed the actions we need to take right into our grammar rules. It's like putting little instructions inside the blueprint. For example, we could have a tiny action that just says print a minus sign right at the moment the computer sees a subtraction.
And this comparison makes it super clear. On the left, the definition is all about the what. It describes the final result. But the scheme on the right,
That's all about the how. It gives a direct order. It says, hey, after you've dealt with the expression in the term, do this one thing. Print a minus sign. It's a shift from just describing a thing to giving a step-by-step recipe to build it. It's a small change in notation, but it's a huge change in perspective.
So let's just take a breath and put this all together. What we've really been looking at is this incredibly elegant and systematic way to translate, well, any language that has a structure. It could be simple math, or it could be an entire programming language.
And it all boils down to this simple three-step pattern. First, you define the structure. That's your grammar. Second, you attach meaning to that structure. Those are your definitions. And third, you embed the actions right inside. That's your scheme. That's it. That's the whole dance.
And when you really think about it, this reveals something kind of profound. We say a computer understands code, but does it really? Not like we do. It doesn't have a sudden moment of insight. It's just methodically, tirelessly following this elegant set of rules that we've attached to a structure. It's a beautiful mechanical ballet.
And that process, the idea that you can build something incredibly complex, like a whole programming language, or the design for a chip, just from a handful of simple repeating rules, I mean, that's truly one of the most foundational and I think one of the most beautiful ideas in all of computer science. It's this quiet, powerful engine that just hums along in the background, making so much of our modern world possible.